Hello everyone and welcome to this video where today we're going to be deriving the complex representations of sine and cosine, which will then allow us to find everyone's favorite formula, Euler's formula. So we'll actually be starting off by finding the complex representation of arc sine and cosine, or the inverse, and then we'll be able to work from there. So this probably isn't the most efficient derivation formula for Euler's formula, which we'll be finding in the end. Traditionally you'd be working with the Taylor series expansions of the sine and cosine function and doing some algebra from there. But this is something I came up with a couple of years ago and I really think it's quite interesting, so hopefully you enjoy. So we're actually going to start off with an integral, namely the integral of 1 over the square root of 1 minus x squared dx. And if you're familiar with your derivatives and integrals, you would know that this can immediately be evaluated as the inverse sine of x plus some arbitrary constant. But at the time when I came up with this derivation, I was learning about some trigonometric substitutions and I was thinking of a way to make a substitution here and evaluate this integral differently so that we can compare it with the inverse sine of x and find some relation from there. So what we're going to do, since we're working with complex numbers, is we're first going to change this expression and introduce the imaginary unit I. And the way we're going to do that is by, instead of writing 1 minus x squared, we'll write 1 plus ix all to the power of 2 dx. And this works because the 2 will be distributed to both this I and x, and by definition of I squared is negative 1. And so we end up with this original expression, so that works out. Okay, next let's make our substitution. Now if you're familiar with your trigonometric identities, you would know that 1 plus tangent squared is equal to secant squared. So let's let this ix here be equal to tangent of some new variable, let's say theta. And usual business with the substitution, we'll now evaluate our differential dx. So x will be equal to 1 on I tangent theta, and dx will be equal to the derivative of tangent is secant squared theta, d theta. And I'll also rewrite this 1 over I as negative I by multiplying the numerator and denominator by I. Okay. So let us now substitute in these expressions and change our integral into our new variable theta. So we're going to have the integral 1 over square root of 1 plus tangent squared theta multiplied by negative I secant squared theta d theta. Okay, as previously mentioned, this 1 plus tangent theta is nothing but secant squared theta. So we have the square root of secant squared theta, which I think technically should be the absolute value of secant theta. But if we just cancel out the square root and the square, we will end up with secant squared in the denominator. So this whole denominator here, including the square root, is just secant theta. So that secant theta will be cancelled with one of our secants up here. And so we'll end up with integral of just secant theta d theta, and I'm also going to take this constant negative I out the front of the integral sign. Okay, from here, the integral of secant theta, if you're familiar with it, it is the natural log of secant theta plus tangent theta and plus some arbitrary constant. I'll call this C2, call this C1, because so we don't get confused between them. Yeah, and now the way you evaluate this integral is you multiply the numerator and denominator by this factor. I'll leave it to you if you want to know more details about that. Now we need to transform our answer here back into our original variable, namely x, rather than theta, and the way we do that is by drawing a triangle here. So if we draw a right angle triangle with our angle theta here, we know that tangent theta is equal to ix, so we can write an ix here and a 1 here. and applying the Pythagorean theorem, this hypotenuse will then be 1 minus x squared. Okay, now we can rewrite this expression in terms of x using this triangle, and we'll end up with negative I times the natural log. Secant is the reciprocal of cosine, so it will be the hypotenuse over the adjacent, namely square root of 1 minus x squared, plus tangent theta, which we said was ix plus c2. Okay, now we can compare this expression which we've derived to our original expression which we wrote by definition. So this is equal to inverse sine of x plus c1. And if we let x be equal to 0, we can actually compare these constants and go from there. So obviously here, if x is equal to 0, this is going to be 0. This whole thing is going to be 1, so it's going to be natural log of 1, which is 0. So this whole thing is 0, inverse sine of 0 obviously is 0, and we'll just end up with c1 is equal to c2. So we can actually cancel out these two constants, and we will arrive at our first conclusion, which is that the inverse sine of x is equal to negative I multiplied by the natural log of 1 square root of 1 minus x squared plus I times x. Next, using our previously derived expression for the inverse sine of x, we'll now be finding the expression for the inverse cosine of x. And the way we'll be doing that is by applying this identity that the inverse sine of x plus the inverse cosine of x is equal to pi on 2 radians, or 90 degrees. And you can prove this identity by drawing a right-angled triangle with hypotenuse length 1. But the key thing to note here is that pi on 2, another way we can write that is the inverse sine of 1. So here we have an equation with 3 terms, 2 of which are expressed in terms of the inverse sine function, and we already have an expression for that. So all we need to do is rearrange for the inverse cosine of x, and then we will have our expression. Namely, inverse cosine of x equals the inverse sine of 1 minus the inverse sine of x. Here we can apply our formula, and for the first term, all we need to do is substitute in x equals 1, namely negative I multiplied by the natural log of 1 minus 1 squared plus I times 1. And for the second term, we will have minus negative I times the natural log of 1 minus x squared plus ix. Here we can now do some simplifications. First of all, this 1 minus 1 squared in the square root, that is all 0. So we can simply write that as minus I times the natural log of I. And this double negative will now become positive, so plus I times the natural log of 1 minus x squared plus ix. Now we can apply our logarithm laws. If we have two logarithms being added or subtracted, we can combine them together with their arguments being a product or quotient. So in this case, we will have I times the natural log, and we will have our second term here, 1 minus x squared plus ix, being divided by this the argument of this first logarithm here, I. Now we can just split this fraction, and we will have I times the natural log of 1 minus x squared on I plus ix on I, where obviously for this second term the i's will cancel. I will also rewrite the denominator I of this first term as the square root of negative 1, and by doing that we can combine this square root, and it will have the effect of multiplying this term inside by negative 1. So we will have I times the natural log of square root of now x minus 1 plus x. And here we have our second conclusion, that the inverse cosine of x is equal to this expression here. Next, using these expressions which we've derived for the inverse sine and cosine, we'll now work with these to find the regular sine and cosine. Now the way we'll do this is by calculating an inverse of these expressions. We'll start off with the sine. So what we'll do is we'll let y be equal to this expression which we've derived, which is negative I times natural log of all that. And to calculate the inverse of this expression, all we have to do is switch the x's and y's, and that will have the effect of flipping this graph along in the Cartesian plane along the line y equals x. So to find the inverse, we will just replace the x's with y's and the y's with x's. So we'll just rewrite this out. And now we'll do some algebra to express this in terms of just y. So let's first of all divide by negative I on both sides, and having a negative I in the denominator is the same as just regular I in the numerator. So we will have I times x on the left hand side, and that'll be equal to the natural log of all this stuff, y. Next we will raise both of these sides of the equation as an exponent to the base e, so that we can cancel out this e and this natural log and have this expression now. Next we'll move this iy over to the left hand side of the equation and square both sides to remove this square root. And then we'll expand out this left-hand side. Here we can see that the y squareds will cancel out. And let's now move this one over to the left-hand side and this expression over to the right-hand side. Now all we have to do is divide both sides by 2i e to the power of ix. And by dividing this e to the ix in the numerator for both this term and this term, we end up with our final expression. So this is our conclusion for this stage. We have derived the fact that sine of x is equal to e to the ix minus e to the negative ix over 2i. And you should be familiar with this expression if you've studied complex numbers before. Next, we will apply the exact same strategy to find the cosine of x, and I'll probably just speed this bit up. Finally, we can work with these two expressions for sine and cosine of x and derive Euler's formula from there. So what I'll do first is multiply both sides of the sine expression by I, so that we have a common denominator 2 between both expressions. Next, I'll add these two together so that we'll get some cancellations happening. So I sine x plus cosine of x is equal to, now because both have a common denominator, we can write all of this in the numerator. And then we can just collect the like terms and cancel out some things. So these two terms with the power negative ix, they will cancel. These are repeated, so we'll have 2 times e to the ix, but then we have a 2 in the denominator. So this altogether is just equal to e to the ix. And here we have it. We've derived Euler's formula. E to the ix is equal to cosine of x plus I times sine of x. And of course, you may be familiar with the famous identity. If you let x be equal to pi, then you can get this expression, e to the I pi plus 1 equals 0. This is another famous expression, quite a beautiful equation. You may have seen that YouTube video, Most Beautiful Equation in Math. But yeah, that's about it. So I hope you guys enjoy the video. Maybe you learnt something, and I'll see you later.